Good morning, everyone. Welcome to our presentation. Today, we are excited to share with you our work on fluorescence spectroscopy. This is the cover slide, so I'd like to briefly introduce what you can expect. We will be discussing the fundamentals of fluorescence spectroscopy, its applications, and our research findings. I'm pleased to be guided by Dr. Aishwarya Balap and our talented team members Vrundali Campbell, Vaibhav Jagtap, Yashpal Jamadar, Achal Jain, and Khushboo Jumade from Pisa's Modern College of Pharmacy, NIGDI. Let's get started. Let's take a closer look at fluorescence, which is actually a specific type of luminescence. It occurs when a substance absorbs light energy, usually ultraviolet or visible light, and then emits light at a longer wavelength. This process involves several key steps that are quite fascinating. First, there's absorption. A molecule, often called a fluorophore, absorbs a photon of light. This energy excites an electron, moving it to a higher energy state. Think of it as giving the electron a boost, lifting it up to a more energized level. Next, we have relaxation. The excited electron doesn't stay at this high energy level for long. It quickly loses some of its energy through vibrational relaxation, which basically means it relaxes to a slightly lower vibrational energy level within that excited state. Finally, the electron returns to its ground state, releasing the remaining energy as a photon of light. That's what we see as fluorescence. This emission of light at a longer wavelength is what makes fluorescence a powerful tool in spectroscopy. Understanding these steps helps us grasp how fluorescence spectroscopy works and why it's so useful for analyzing various substances. Let's take a closer look at the Jablonski diagram. This diagram is a fundamental tool for understanding how molecules absorb and emit light. It visualizes the different electronic states a molecule can occupy and how it transitions between these states. The key points here are the excited states, which are higher energy levels, and the ground state, which is the molecule's lowest energy state. When a molecule absorbs a photon, it jumps from the ground state to an excited state. From there, it can relax back down through different pathways, including fluorescence or phosphorescence, emitting light in the process. What makes this diagram so important is that it connects the energy levels to real-world phenomena like fluorescence, which is the basis for many imaging and sensing techniques. By understanding these transitions, we can better interpret how molecules behave under various conditions. Overall, this diagram helps us visualize the complex processes of light absorption and emission in a simple, clear way, reinforcing the overall theme of understanding molecular interactions with light. Let's talk about fluorescence lifetimes and quantum yield. Fluorescence lifetime is essentially the average time a molecule stays in its excited state before emitting a photon. It's called the intrinsic or natural lifetime because it reflects the number of photons emitted in the absence of any radiative processes that might quench or interfere. Think of it as the molecule's natural clock, showing how long it can stay excited under ideal conditions. The lifetime of the fluorophore depends on this ratio of the number of photons emitted to the number absorbed. Now, moving to quantum yield. This is a key concept because it tells us how efficiently a fluorophore converts absorbed light into emitted fluorescence. A high quantum yield means most of the absorbed photons are re-emitted as fluorescence, which is crucial for imaging and detection purposes. Connecting these ideas back to our overall theme, understanding fluorescence lifetime and quantum yield helps us optimize our use of fluorescent labels in various applications, ensuring we get the best signal and the most accurate results. Let's take a closer look at instrumentation. This is a crucial part of any project because it involves the tools and devices we use to measure, monitor, and control different variables. Essentially, instrumentation is what allows us to gather accurate data and ensure everything operates smoothly. When we talk about instrumentation, we're referring to sensors, gauges, and control systems. These are the backbone of our ability to make informed decisions. Highlighting the most important concepts, it's key to understand that good instrumentation improves precision and reliability in our processes. It also helps us detect issues early before they escalate, saving us time and costs. As we connect this to the overall theme, effective instrumentation ties everything together. It's what transforms raw data into actionable insights, driving efficiency and safety across the board. Let's talk about the detector, which is a crucial component in our system. First, it's responsible for identifying the signals or data that meet certain criteria. Think of it as the gatekeeper, ensuring that only relevant information gets through. Next, its sensitivity is key. If it's too sensitive, we might get false positives. If it's not sensitive enough, we could miss important signals. That balance is essential for optimal performance. Then, we have the accuracy of the detector, which directly impacts the reliability of our entire process. It's designed to distinguish true signals from noise, which is vital for making correct decisions downstream. Lastly, the detector's integration with the rest of the system ensures smooth operation, allowing us to process data efficiently and effectively. Overall, a well-designed detector is fundamental to the success of our system, tying together accuracy, sensitivity, and reliability to support our larger goals. This slide doesn't contain enough information. That's why we're moving to the next slide. Now, let's explore some key pharmaceutical applications of our techniques. First, they play a crucial role in the identification and purity testing of drugs, ensuring that what reaches patients is safe and effective. This is vital for quality control in the pharmaceutical industry. Next, these methods help detect drug, protein binding interactions, which are fundamental in understanding how drugs work in the body and can influence drug design. Lastly, they are instrumental in studying how drugs are released and absorbed, providing insight into their effectiveness and optimal delivery methods. Moving on to environmental monitoring, these techniques are essential for detecting pollutants like PAHs or polycyclic aromatic hydrocarbons, which are common environmental contaminants. They also help monitor water contamination and oil spill residues, enabling us to assess environmental health and respond quickly to pollution events. Overall, whether in pharmaceuticals or environmental science, these applications highlight the versatility and importance of our analytical methods in safeguarding health and the environment. Thank you so much for your attention. I really appreciate you taking the time to go through this presentation with me. It's been a great opportunity to share these insights and ideas. Remember the key points we discussed, whether it's the importance of innovation, collaboration, or adaptability, are all crucial to achieving success in our field. I hope you found this as inspiring and useful as I did in preparing it. Feel free to reach out if you have any questions or want to continue the conversation. Again, thank you very much for being here and for your engagement.